Hey everybody, this is our chapter 17 video, Electrochemistry. Electrochemistry really is that area of chemistry that looks at the transformation between chemical and electrical energy. The idea here is we got two real systems we're going to look at, these electrochemical cells. The majority of the chapter, majority of what we're going to focus on, are what we call galvanic or voltaic cells. These are our batteries. These are chemical reactions that produce electrons spontaneously in the process of forming products. And those electrons are being transferred when I say they're being produced. They're transferred from one species to another. If we harness that, we can drive something and power something. That's the essence of a battery. These spontaneous reactions is galvanic or voltaic cell. Same thing, just two different terms to refer to it. At the end of the chapter, we'll introduce another electrochemical cell called an electrolytic cell. These are the ones that are non-spontaneous, but we're going to use electrical energy to do work to drive those reactions. But before we jump into electrochemistry, we really have to review redox. So let's take a look at what redox is. Redox is just short for reductions and oxidation reactions. And these are two half reactions that always occur simultaneously. And that's because we can't have electrons just flying around loose in systems. The only place that happens is in plasmas. So reduction is the gain of electrons. These two definitions are the best. They include everything. There's other definitions out there. And that definition might seem confusing to you. You say reduction is gain. Well, that's confusing. Why didn't we just call that oxidation, a reduction loss? Well, it refers to the oxidation number. It's a reduction in the oxidation number. We'll see that in a second. But they always occur together because whatever electrons are lost have to be gained by something else, and therefore the reactions have to be balanced. So if you were to start with, say, a system like this, where you had maybe copper ions, and let's do copper +1 ions in aqueous solution, and zinc solid. And what happens is we go to zinc 2 positive in aqueous solution, plus copper solid. So you can see the copper has picked up electrons, gain of electrons. It's being reduced. Its oxidation number is going from +1, it's understood to be 1, to 0 because that's elemental. That's the reduction that we're talking about. And the zinc's going from 0 to +2. Well, that's not a balance of electrons. Something's wrong here. Well, that's because we're going to need 2's out in front of the coppers. That always has to be balanced, the number of electrons. So we'll do this in class too. When you see a half reaction, you might have to multiply it by something to balance those electrons. But in this case, zinc's being oxidized, copper's being reduced. Now, it's not always easy to see the electrons like there is here because we've got charges. But what if you had something like this? What's being oxidized? What's being reduced? We go back to those rules that we have, and they're in Chapter 8. We say that oxygen pretty much is always -2, right? Except for in peroxides. We're not going to worry about exceptions. Now, this is elemental oxygen, so this is 0. And this is elemental carbon. This is 0. The other rule is that, carbon you just got to figure out. So you go with the rules that tell you the ones we know. Oxygen's pretty much -2. Fluoride's -1. Any ions are their charge. Sodium ion is +1. So that's the way you do it. Halogens are typically -1, but not always. So what we're going to do is to say oxygen's -2 over here. That means it became reduced because it went from 0 to -2. And since there's 2 of them, there's 4 electrons that have been transferred here. You see that? And carbon's going from 0 to 4+, then. It has to be. That's what you're doing. We're using that to figure out. So that comes back. You're using that to figure out how many electrons are being transferred, what's being oxidized, what's being reduced. So you have to go back and learn your oxidation numbers. And the way we did this, we did things like this. This is nitrate. What's the oxidation state? That's kind of like the theoretical charge. That's what we've been doing here, this oxidation number, oxidation state on nitrogen. Well, we know that the total charge is -1. That's what this is up here. That has to equal to the charge on the nitrogen plus the charge on the oxygen. Now, there's 3 oxygens, and we learned that it's always -2, so that's -6. Do the math. Nitrogen must be +5 in order to get -1. That's how you figure out oxidation numbers. That's what you're going to need to use to figure out what's being oxidized and what's being reduced. Okay, so that's oxidation reduction. Reduction is gain of electrons, but it's a decrease in the oxidation number. Oxidation is the gain of electrons. I'm sorry, loss of electrons, and it's increase in that oxidation number. The other thing we tell people to look for if it's a complicated reaction is oxidation is the gain of oxygen. Reduction is the loss of oxygen. Or another way to look at it is reduction is the gain of hydrogen in some cases, acid-base reactions, and oxidation is the loss of a hydrogen. But the electron one is always a foolproof definition. But sometimes if you need to look for something, that comes in handy. Now here's a case where we've got copper 2 positive, so the electrons are balanced. The overall reaction then is copper 2 plus ions going to copper solid, and zinc is going off into solution. That's what you see here. This is zinc metal coming off into solution, changing the color. The copper is the blue color, and the ions are depositing actually on the surface here, and you can see this surface is getting coated. So we create these electrochemical cells. When you create an electrochemical cell, you're going to have an anode, a cathode, and a salt bridge. Now, the anode is where oxidation takes place always. That's just a convention. So in this case, zinc would be oxidized. That would be our anode. Okay, in the convention, that's negatively charged. Remember, reduction is the gain of electrons, so we're going to have electrons moving towards the cathode, generated at the anode, and then the copper being reduced over here, reduction at the cathode. The salt bridge is to make sure we have electroneutrality, because what you have to realize is in this beaker over here, zinc ions are being generated. That's going to create a charge imbalance. You can't have that. Think about it. When we make up solutions, we dissolve salts, zinc sulfate, calcium chloride. You don't just put zinc ions in solution. I can put zinc metal. It's not going to dissolve very much. So you have to maintain electroneutrality. So the salt bridge allows us to do that. In this case, they use the sulfate salt. It doesn't matter what the cation here is in case it's sodium. So what's going to happen is there's sodium sulfate here. When zinc is produced here, sulfate ions will move in this direction and move out of this here. And sodium ions can theoretically move in this direction. So basically, and move out of here, keeping that charge balanced. If you have plus charges developing here, we're going to either have to take away plus charges there or add negative charges. And if we have plus charges being consumed here, we've got to replace those or take away negative charges. They maintain that neutral system. And that's key. Salt bridge connects that. Now, there's a notation that's used for writing these cell diagrams. And what you always do is you write the oxidation on the left. So you notice we have zinc on the left, copper on the right. This represents our salt bridge, the double line. The single line is a phase boundary. That's telling us we have zinc solid, which is a solid phase, and then we have zinc ions in solution. 1 molar solution. So that's what that represents. And if you do have certain concentrations, you'll write them in parentheses. But it's showing you how the actual reaction is happening. That's why you write this. Zinc's going to zinc 2 positive, and copper 2 positive is going to copper solid. So that's the way you write it. Oxidation on the left, reduction on the right, with the actual species in the direction they're going. Now, a big part of what I'm going to emphasize in class is this standard cell potentials, standard reduction potentials. And what this is tabulated values of reduction half reactions. It's only the half reaction, and you get a value for that. Now, you might say, well, you can't have a half reaction. You have to have a coupled reaction. This is true, but they're going to all be compared to one other half reaction, and that is this hydrogen. That's our standard. So everything's going to be compared to that. And that's how we're going to get these tabulated values of reduction potentials. This is my table. You won't find this in the book. The one in the book is fine, but it's tough to read, and I don't care for it that much. So I'm using this one for the video. So these are reduction potentials, and this is a really important equation. E stands for reduction potentials. So what you're going to put into this equation is always reduction potentials taken directly from the table and plugged in there. Okay? And what this table is listed as, the larger the value, the higher up, the more easily the reduction goes. the more work you can do with it, if you will, if you want to look at it like that. And it's not surprising at the top of that list is F2, because you know F2 is a halogen all the way to the right. It likes to form the fluoride ion, pick up one electron, that type of thing, right? Likes to react and do that. Of course, fluorine gas, we're not talking about the fluoride element, but still, the fluoride ion is very stable, so therefore this reaction is very, very common and very easily, very spontaneous, very energetically favorable, so it has the highest value on this particular table. That means it's the most likely to proceed as a reduction of anyone on this table. And this is the least likely. And look at what's at the bottom. It's a cation, and it's a metal. We know metals don't like to exist as elemental metals like this. They like to lose their electrons, especially group 1 and group 2, right? And form cations, so they can have their octets. So it's not surprising this value is very negative compared to this value very positive. So this is a reduction potential chart. Now what we're going to do is we're going to couple two reactions. And when you couple two reactions, and if you look here, let's erase all this now. Looking at copper and zinc, which is the ones we've been looking at, there's copper there, there's zinc there. When you couple those, the height on the chart will tell you which one will proceed as the reduction. Copper will proceed as the reduction. That means that zinc cannot be reduced in the presence of copper. It's going to be the one that's oxidized. So if you had a system with zinc solid, zinc ions, and copper ions, this is what's going to happen right here, because the copper will proceed. If you were to put just copper metal and copper ions with zinc ions, nothing would happen. You need the zinc metal to be oxidized. Okay? So that's what this is telling you. And now what you do is you take these values directly from the table, stick them into the cathode and anode, oxidation at the anode, so zinc. What the negative sign does is basically flips this, which because we're flipping the reaction. It's not going to proceed in this direction. It's going to proceed in this direction, which means the sign has to be opposite, just like delta G or delta H or delta S. The signs have to be opposite if for the reverse reaction. So it's telling you which one proceeds as the reduction. The other one must proceed as an oxidation. It automatically flips it for you by just sticking the reduction potentials into the table, giving you a value for that particular cell, which you see right here. Oh, this one doesn't have a voltmeter. Oh, this one right here. So that's the half reaction, half reaction. There's your voltage you get from this particular cell. Okay? So that's the way to use this table, and then we're going to spend some time on that. Now, it's important to realize that voltage is kind of a measure of like that work that you can do. Okay? And we saw that delta G is like that, so it's not surprising. And remember, these E naughts here, these reduction potentials are in volts. That volts relates to delta G, which is work. Now you can write this also as, we'll use it more like this actually. In standard conditions, once again, 25 degrees C, 1 bar pressure, 1 mole concentrations, all of that. But the equation allows you to see that we can relate these two, and you'll just have to use Faraday constant, which is basically 96,500 coulombs per mole of electron. A coulomb is your unit of charge, and a volt is a joule per coulomb. So when you say you have a 60-watt bulb, that means you're using 60 watt joules of energy every second. Okay, I'll come to that in a second. I jumped ahead here. I didn't realize. In fact, it's not even in this video. But anyway, that's what a 60-watt bulb is. I was looking for it, but it's basically joules per second. When you talk about watts, watts is not even listed here. But so I'm jumping the gun. I'll talk about that in class. A watt is a joules per second. I thought that was in here, this slide. All right. So again, how did we get these values here? Well, we're comparing them all. We're going to set up a cell in which copper is set up with hydrogen like this. Hydrogen gas and hydrogen ions. And we're going to measure the voltage. And with copper solid too. Put the whole system together, you measure a voltage, and you get a positive value. That means the copper will proceed as the reduction. the hydrogen reaction will proceed as an oxidation. If I do it with zinc, it's the opposite. That's going to proceed, the hydrogen will proceed as the reduction, the zinc one will proceed as the oxidation. So that's how you determine these values. And that's what we're doing here. We're showing you how these values are tabulated. You set up a cell in each case with hydrogen, but in one case, the anode is going to be zinc. In the other case, the anode is going to be hydrogen, where oxidation takes place. So zinc proceeds as the oxidation when paired with hydrogen, the further one down, and copper proceeds as the reduction when paired with hydrogen, and the hydrogen proceeds as the oxidation. Okay, one of the last parts of the chapter is the Nertz equation. And what that is it allows us to look at the effect of concentration on the E of the cell. So now we're going to look at a system in which, eventually your batteries die, right? Reactants run out. To completely consume the battery's dead, the reaction stops. So we're going to need an equation to tell us how the potential of that cell that we create, that battery is just an electrochemical cell, changes as the reaction proceeds. And that's what the Nertz equation allows you to do. It should look pretty familiar to you, right? E equals E naught plus RT ln of Q, or E equals E naught plus R minus RT ln of Q, right? We just have something in there with moles of electrons and Faraday's. I don't think I mentioned this, but N is number of moles of electrons. So the equation looks very similar, and they relate to each other. E, the cell, is very similar to delta G, and E naught of the cell is very similar to delta G naught. The one changes as the reaction goes, as products form from reactants. The other one is just standardized tabulated values. So it's exactly the same thing. And you can see by looking at this equation, as Q changes, as products are formed, this number becomes larger because that's a numerator, and it's subtracting from the potential. The potential is really the difference between the species, the energy you get by making a pair. It's kind of like a waterfall. How high is your waterfall? If I'm going from here to here, I have a huge potential difference. I can do a lot of work. If I have a short waterfall, here to here, I can do much less work. That's what the potential is. Okay? But as products are formed, that's kind of like, that's a little bit different than a waterfall. Obviously, we got a chemical reaction taking place. It's going to make, there's less material there. It's going to affect your system and slowly start to take away from that potential. It's going to get smaller and smaller. But what we'll learn in class is that really doesn't come into play until you're almost all the way to products, meaning your battery doesn't lose a lot of power until almost all the reactants are converted to products. And it's because the fact that this is log, you can't even see this here, but it's a log relationship. So the E naught changes very little until it's almost all product, and that's when the battery dies. That's really important for batteries, of course, because what you wouldn't want is, after 25% of the reactants have been converted to products, you've lost 25% of your voltage. Well, that's no good. I need 12 volts to start my car, right? 12-volt battery to start my car. No good if I've lost 25% after, a year. So I'm just going to end with this. Just get familiar with this. Make life a little easier for this chapter. In amps, those are amps. Ampere is a coulomb per second. This is where my watt comes in, right down there. So it's the charge per unit time. So therefore, you can just rearrange that and say a coulomb is an ampere second. That doesn't make as much sense to our brains. Amp being a charge per unit time. So if you want to know a coulomb, well, you take your amperage and multiply by the time, and then you just get the amount of charge. Joules are your work. They're your G, right? That's our work. We always use kilojoules a lot for G. And it's a coulomb volt. So since a coulomb is an ampere second times a volt is a joule. And a watt is a joule per second. And that's what I meant by a 60-watt bulb. Uses 60 joules of energy every second. Okay, that's the end of the video. we'll be sure to tackle this in class.